Ladies and gentlemen, good evening once more. I did explain the rules and regulations or how we should behave each other and respect each other in this particular meeting. So basically, this is a continuation of the lesson that we had last week. So I'm not going to elaborate more in terms of the people that are writing on my screen. Musa, I don't know why you are writing on my screen, but I never gave you rights to do so. So this is something that I will not elaborate more on or even further. So starting the lesson, let's start with the basics. The very first thing to do, is muting all of you. And now I have muted myself, you see. Lucky,
Yes, sir.
please mute yourself, sir. Thank you very much. Uh, Last week, what we did was just the basic concepts. And remember, last week we were focusing more on basically how we build the information from grade 10 to grade 11. So the way we wanted to build was we start with the basics such that now our approach to more complex calculations, our approach to more heavy questions is that now we know that with the base, the foundation, each and every one of us now is in the right direction. So today we are going to work more with more complex uh, stoichiometric calculations. But what do they necessarily mean with more complex? More complex, it just means we are going to integrate. We are going now to integrate the basics with things that we are going to add into this particular session. The first one, it says you must be able to determine the empirical formula, molecular formula of compounds, calculate now the percentage yield and now the percentage purity, and thereafter perform calculations based on a balanced chemical equation including the limiting reagents. So that is where we are going. So last week, most of you were very active. I really appreciated that. But now we are in a position of ensuring that we do more of grade 11. And remember, this section of more complex geometric calculations is the session that you are still going to use in grade 12. You are still going to use moving forward, maybe somewhere in your university life, because it's principles, it's concepts that ensures us that the chemistry part of things in grade 12 are done in detail. Because what we do in grade 12 is, remember, we assess everything from 10 to 12. So now it means this section, it's more important because we use it everywhere in chemistry. So I'm going to try by my level best to give you the little that I know. Some of you have done this already at school, it's fine, but believe you me that the approach, like I always say, will definitely be different. So this is what I intend on us arriving, or at the end of this session we should have been able to do each and every bullet thereof. Remember, these bullets are from the exam guideline, these bullets are from the CAPS document. So it basically says each bullet will now be part of the examination. So once we have now ticked all the check boxes, then we are able to say we are ready now for this particular examination. So without wasting time, let me just try muting these people. Okay, no, let's start. So the very first one that I want us to start with is percentage composition. So now, okay, black. The first one that I want us to start with is percentage composition. Composition. But what is it that percentage composition is telling us? Basically, percentage composition informs us on what percentage does each what percentage does each element informs us on what percentage does each element consist in terms of the arrangements of the atoms. So element each element consists in a compound. So we will have our compound, yes, but now from the compound we want to know what is the percentage of each element in that particular compound. So basically what it says is, if I have a compound, remember a compound now, it's a substance that consists of two or more elements. So if I want now to check what is the percentage contribution of this particular element, and basically focusing on the percentage composition. But now, how best can one go about finding and ensuring that we calculate now the percentage composition the right way? The first thing to do is you will have your molecular formula. So this is now the molecular formula. So when you have your molecular formula of a compound, molecular formula of a compound, then the molecular formula obviously will inform us in terms of which elements do we have. So I am going to say the molecular formula will tell us which elements make up the compound. So what is this molecular formula? I will explain as we further move on. But now, once I have identified which elements makes up the compound, what will be next? The next step now is I will have to move in this one, which will be my step number one. Step number one, I must now determine the molecular mass. Molecular mass of each compound. Fine. Each compound. That will be my step number two. So I have identified the elements. Thereafter, I now determine the molecular mass of each element. So it's not a compound but an element of molecular mass of each element, because I have already identified the elements that makes now the the compound. So it says to me, fine, if now I have determined the molecular mass, how is this going to assist me? This is going to assist me because I will know now the molecular mass of this particular compound and now the total of the compound. So step number 2 in this case will be now calculating the molecular mass. That is number 2. Calculate the molecular mass of the compound. So I have now 2 points where I will say, fine, this, let me just call it an X. Allow me now to call this one Y. This one, which is the total. This computer is slow, guys. If you have money somewhere, please donate one for me. So this one will be your Y. Then I have X and Y to simplify this analogy that I want us to work with. So from this, I can easily say, but what must I do hereafter? What will be my third and final step in this case? In this case, I'm going to say I must have now percentage of element is equals to number of atoms number of atoms multiply by the molecular mass of an element divided by now what? By now the total molecular mass. So I must emphasize this must be total molecular mass of the compound. So can I write it in simple form? Because it's percentage, I must create space now here to multiply by 100, because now the mathematics has taught us that if we want percentage, everything must be multiplied by 100 to give us the percentage. So already this is a hint for me in an exam. If I have a compound and I calculate each and every element, how much percentage it's contributing, what will happen to me? It's very easy. I will be in a position of ensuring that the sum of each element or the total elements I have must add up to 100. If they do not add up to 100, it means somewhere, somehow, there's a mistake now that I did. So it is very, very crucial and important to realize that the best way of ensuring that everything is done the right way is by ensuring that the sum of each percentage that you got from calculating for each element must be now equals to 100. If not, then it basically says something is wrong. So I'm going to write it in red because remember, this equation here, it's not part of the formula sheet. It's not. So how best can I remember this? It's very easy. I added now the y and the x for this particular purpose. So what else can we do? We can simply write it now in a simpler form for us to be able to remember in an exam. The idea here is ensuring that we remember in an exam, because the exam or the test that comes will not give us now this particular formula. So to accommodate the number of atoms, I will say X is the molecular mass of an element. Y is the total molecular mass of the compound. So this allows me to be in a position of saying X over Y multiplied by 100. So I'm in a position of saying percent of element must be equals to AX divided by Y multiplied by 100. So what is A? A will be just now the number of atoms. X will be now what? The molecular mass of an element. Then Y will be the total molecular mass of a compound. So by so doing, I've minimized the science. I've minimized the complexity of me not remembering everything that has been expected for me to know in terms of the percentage composition. So the examples of it, the questions there of it, they are basically the same throughout. They are basically the same in a position, in a way of, once we understand fully how to apply this particular analogy, then we are in a position of 100% we are going to be right. So this is the basics that I want you to take from this. Remember, we'll also share this particular notes in our WhatsApp group immediately after the session. So if you feel that maybe I'm somehow quick for you, no problem at all. You can ask questions. I see Manuku. It's saying something. Manuku Makama. The platform is yours, me. Before I move to the other slide.
Sir,
Manuku.
those two, sir,
Yes.
those two steps you mentioned over there, are they part of the formula, or do we do them aside before we substitute in the formula?
Thank you, Manuku. Good question. Now, remember to lower your hand, ne? Now, depending on mark allocation, I usually say you are reporting to somebody that does not know science. Or if this somebody knows science, it's always nice to explain the science in detail. So if it happens that you come here and just say 2 multiplied by 56 divided by 185, the question will be, where did you get those numbers you are working with? So preferably do number 1, determine now the molecular mass of each element. Do number 2, calculating the total mass or the total molecular mass, of which is what we did now in the previous session. Then you have everything in front of you, then it's just substitution. Even if it happens that it becomes 6-7 marks, it means I'm expecting to get information from 1 and information from step number 2. Then you can use the formula. Let's do our science in such a way that it's informative. Let's do our science in such a way that even the person who is not in this particular class and receives the notes, or you want to explain, they will fully understand. That is what we are trying to do here. So in simple English, Manuku, what we do is write everything. Step 1, show how you got your molecular mass of each element. And when do you get that? Simple, the periodic table which is given. How do you calculate the total molecular mass of a compound? You use the same principles you used last week. Then where did you get the number of atoms? From now the molecular formula of the compound. It's as simple as that. So kindly do it now step by step, such that we know where and how you got to your final answer. So moving further on, I have a question here that I found somewhere. It says now determine the percentage of iron in iron oxide. Determine the percentage of iron in iron oxide. So this one I will do it as an example. So we are calculating the percentage of iron in iron oxide. So we are going to do it in simple steps. Step number 1, we have our molecular formula, which is iron. So this is our molecular formula. Very happy. Step 1, identify or determine the molecular mass of each element. So how many elements do I have here? I have iron, I have oxygen. So it's basically 2 elements. So I'm going to determine the molecular mass of iron from the periodic table. The periodic table I have here says it's 56 grams per mole. Then I have molecular formula of oxygen. It's 16 grams per mole. So I am done now with step number 1. Step number 2, calculate the total molecular mass. So total molecular mass will be iron 2O3, which will be 2 multiplied by 56 plus now 3 multiplied by 16, which will give me something like I have a calculator here. Yes, calculator. Let me put it here. It's 2 multiplied by 56 plus now 3 multiplied by 16 will give me something like 160 grams per mole. So 160 grams per mole. Then I am done with that. So where do I go now? I go to my formula. My formula says now percent of element. Percent of element, but now which element specifically now? The question was clear to say we are calculating for iron. Then we say it's the number of atoms multiply now by molecular mass of element divided by molecular mass of compound, because now the formula is not in the formula sheet. There is no mark for that, unfortunately. Then it's equals to how many atoms do I have for iron? I have 2 atoms, which that is now 2. Then what do I have as my molecular mass? It's 56 divided now by 160, multiply by 100, multiply by 100. Then I have my final answer for iron as now 70%. I see here in the chat room, Musa says it's 35%, and then like Mashinini says it's 70%. So Musa, if you got the 35%, it's because now you did not consider the number of atoms. So once you have missed that part, automatically everything is going to be wrong. So it is advisable to now know that this particular formula, which will not be part of the exam, it has now this section here of the number of atoms. So the correct answer here is 70%. Thank you. So Musa, kindly ensure that you don't miss any part of this equation, especially where you need now to focus on the number of atoms. So the number of atoms influences now your final answer. Influences your final answer. So now I have another question. So for each question, I'm going to highlight the compound that the element that you must calculate the percentage composition for. We only calculate for that one because the procedure and the approach is basically the same. So I am going now to give you or highlight the compounds that, or elements rather, that you need now to calculate for. And this should be done in the next 4 minutes. So the first one will be for copper. And then the second one will be for oxygen. Will be now for oxygen. So those are the two ones that we are calculating for. And now remember, I have my timer here. So my timer will be exactly 4 minutes for both of them. Then your time starts now. Remember, share your answers in the chat room. And today I'm doing it differently. I'm going now to ask someone to try and explain all this. So if your answer is correct or if it's wrong, then I'm going to try and give you an opportunity for you to answer. Let me check the answers in the meantime. And tab 8 says they can't hear anything. If that's the case, kindly leave the session and rejoin again, please, because the problem is not on my side, because everybody else can clearly hear me. I'm waiting for your answers, guys, for copper. Okay, answers are coming. Answers, guys, answers. Don't remember, we still have 1.2 to attend to, ne? And we only have 1 minute and 45 seconds. One point two, 1.2. Thank you very much, guys. I'm no longer accepting answers. The ones I received, most of you said copper should be now 39.81%, and then oxygen should be 40.51. So I'm very happy with the answers you got. So it basically says you worked through it. So remember, in an exam, you will be given one periodic table. That I need to emphasize. So now maybe one is looking at a different periodic table and other is looking at a different periodic table in this case, or others are just using the textbook for that matter. So we will get standard answers in an Excel because we'll be using one periodic table for that matter. So all I'm saying is now don't worry if you see the decimals are not the same. Others got 39.94. It does not really matter. It's just an issue of rounding off as well as the periodic table that you are currently holding. So I will share the periodic table that I want you to have, but now it will need you to print or move between the screens. But now for the purpose of this lesson, let's just explain the concept, and then moving forward we'll definitely know what to use. Now for copper, the first thing is to calculate the total molecular mass. Okay, fine, we'll say, man, let's change the pen. Let's change the pen and we say M of copper. It's something like Where is my periodic table here? Let me check my periodic table. I don't know where I placed it. The periodic table. I don't see it, guys. Can somebody give me what's the molecular mass of copper? Is it 63 point something?
5, sir.
How much is it? 60?
63,5.
63,5 grams per mole. And then M for sulfur is equals to, I don't see my periodic table. How sad. Oh,
So for sulfur, it's 32,1.
32,1 grams per mole. And then M of oxygen, it's 16, but now we'll have to multiply it by 4, no problem. So what will be the total molecular mass? Let me just write it nicely.
Would you like to answer?
Wait. Let me get my computer responding well. Okay. Yeah. Okay. M of copper sulfate was the final answer.
159,6
159, comma
6
6
grams per mole.
grams per mole. So the percentage of copper will be now 1, because we only have 1 copper, multiply by 63.5, divided now by the total, which is 1596, multiply by 100. Then our final answer should be 39,81. So it's 39,81%. So I saw most of you got that answer. Thank you very much for all the right things you're doing. So let's go to this one. So with this one, M of K is equals to, and then M of Mn is equals to, and then M of oxygen is equals to 16 grams per mole. So what is M for K?
For K, sir, that's 39,1.
39,1 grams per mole. And then for manganese,
that is 54,9.
54,39. Okay, then
9.
yeah, so M of K, Mn 04 should be equals to, what is the final answer?
That is 158.
148.
158.
158, comma something, or just 158?
I think I disregarded that, but
Okay,
it's
no,
probably comma something.
okay, it's fine. And then the percentage now of oxygen, it must be 4 multiplied by 16 divided now by 158, which will give us something like 40,51%. So this should be our final answer. So there isn't any other complex issue about percentage composition, to be honest enough. The only thing that I want you to understand is the steps of how to go about everything. Ntabiseng Chabalala, your platform is yours.
Sir, I was on the question of 1.2 where we said the molecular mass of manganese is 54,39, which is supposed to be 54,9.
54,9.
Yes, sir.
Okay.
But on my
Let me correct it.
periodic table, it's
54,9.
yes,
On
sir.
your side
It's
is?
just the difference of periodic table.
Yeah, it's just the
55.
difference. 55.
Yes, sir. It's just the
Okay.
difference in periodic tables.
100%. Hence, I explained that your answer in this case will not be influenced by the approach. It will basically be the periodic table that you have in front of you. So I'm going to give you some 5 minutes again when I've explained everything so that I can find my periodic table as well, because I cannot work without a periodic table. It is a key thing to have. And then Mr. Mochichi is saying, say, I don't understand, how do I calculate the number of atoms? Okay, Mr. Mochichi, it's very easy, sir, because let's say you have, I'm going to make it very simple for you. I'm going to make it very simple for you, Mr. Mochichi. It's something that you don't have to worry about. You will see it by just merely looking at the molecular formula. So the easiest way is you just check how many or what is the arrangement of atoms. For instance, let's say we have H2O. So H2O, Mr. Mochich, it says now for hydrogen, how many do we have? We have 2. For oxygen, how many do we have? 1. So these are the numbers that correspond with the number of atoms in this specific compound. So for oxygen, we only have 1 oxygen. But if we have now C4H6, how many carbons? Carbon 4. How many hydrogens? 6, Mr. Mujij. So this is just an easy way of you ensuring that you know what to substitute here for the number of atoms. So it will be just a question of uh, looking at the molecular formula, and then the molecular formula will give you the elements that you are going to work with, such that you consult the periodic table. At the very same time, it will give you now what? The number of atoms. Hence, the first thing that I started with was now the molecular formula. So the molecular formula indicates which element makes up the compound, but the very same molecular formula assists in terms of getting now what? The number of atoms. Remember, now we will be given a formula in this particular fashion. We will be given a formula in that particular fashion and a formula in this particular fashion. So by just looking at it, I have 2 iron atoms, but I have 3 oxygen atoms. I look now at copper sulfate, CuSO4. So I have 1 copper, I have 1 sulfur, and then I have 4 oxygens. I have 1 potassium, 1 manganese, but now 4 oxygens. So basically, that I get from where? From the correct molecular formula that is given to me. Hence, the first step here was I write down the molecular formula. So once you have the molecular formula, 100%, everything will be based on that. Your elements, you get there, the number of atoms. I did not add it as part of the step, but 100%, it's step number 0, because it will be given in the formula, not the formula sheet, but the stem or the statement of the question. Mr. Mochichi, I hope I answered you correctly. And then let me attend to Oluhle Mountain. Will I get marked wrong if my final answer is rounded off to the nearest 10? Oluhle, we are going to give you 0 for the final answer. Yes, 0, Oluhle. The reason for that is, yes. Why are you guys laughing? It's true. We are going to give you 0. So I must emphasize. The reason why, Oluche, we are giving you 0 is because remember, the instructions that you don't read in a question paper says round off to 2 decimal places. So if you have an opportunity of writing 2 decimal places, write the 2 decimal places. So if your answer is 9,50, then you want to say the answer is 10. We are going to give you now raw, because we said round off to 2 decimal places. So if the answer is 39,81, then you want to round off to the nearest 10, which will be 40. We are going to give you a wrong mark. Oluche, I hope you get it now. Mr. Mocheche Khotso, I see your question again. Let me try to follow up on it. I still don't understand how many atoms are there in copper sulfate. Okay, Tate Mocheche, let's look at copper sulfate. Let me remove this, and then we write copper sulfate for you. CuSO4. That is the formula for copper sulfate. So for copper, we just read it from the formula that demonstrates. So for copper, how many coppers do we have in simple terms? Just 1. How many sulfur do we have? Just 1. But how many oxygens do we have in the demonstration? 4. So these are the numbers that we are going to substitute as the number of atoms. So you basically look at the arrangement and the number of atoms that makes elements. Remember, in this case, we are interested in percentage composition. But if we're going to calculate the number of atoms using that Avogadro number, the question will clearly state calculate the number of atoms. So in this case, we are just looking at the formula that is given and now the composition or the elements that makes up now the compound we are looking at. So don't confuse it, Mr. Mocheche, with the one of Avogadro number. Like you will want maybe to calculate the number of atoms using the Avogadro number. No, in this case, we will not use that one, because remember, we said now composition is just informs us on what percentage does each element consist in a compound. So this particular slide is the very most important slide for us to be able to understand 100%. So I hope that Mocheche, I've answered your question and you are in a position of fully understanding. So I am not sure, just by sending a message or something that Mocheche, make me just aware that I can move on, or you are fine now with this small explanation that I have given you.
Sir.
Yes, is this Mr. Mocheche?
Yes, sir.
Yes, Mr. Mocheche, how can we help you, sir?
Sir, I still don't understand, sir.
Okay.
In copper sulfate, right? In copper sulfate, How many atoms do we have?
Okay.
In that molecule, how many atoms do we have?
All right. Simple answer. Remember, now we are specific in terms of what percentage of which element do we want to calculate. Ne? The question is
Brilliant.
completely different from us saying calculate the number of atoms in copper sulfate. So once they now make it a unit for us to calculate the number of atoms in copper sulfate, it takes us back to the things we did last week on how to calculate the number of atoms using the Avogadro number. But for percentage composition, we are interested in how each element, what is it percent inside the copper sulfate. So it basically says we are only looking at copper as an individual element. We are only looking at sulfur as an individual element. So the atoms that we are talking about is the arrangement of atoms that makes up now the compound. So if I have, let me move a little bit to a new page, sorry, let's go back. Like I said, here in Tatemochichi, we are interested only in how much percent is copper contributing to the whole compound, which is copper sulfate. So we look into this number of atoms. Maybe I must also highlight it here. It's basically contribution of each element in regard to compound arrangement. So the way the compound is arranged is what will inform us in terms of the number of atoms. So if I can even change it, I want us to look at this one, Mr. Mujij, and everybody. If you have your mic on, kindly switch it off. Let's look at this one, Mr. Mujij, which is C4H6. I'm going to pose now two questions. I will write it in yellow, but this yellow is not nice. Let's write it in red. I'm going to write it in red, and then the first question is calculate the number of atoms. The second question says calculate the percent composition of that, or just percentage composition. It's better to say percentage composition of what we don't know. So now let's look into it. Everyone assist me here, and I want to clean up the misconception. Already it's a misconception because one will want now to go and calculate the number of atoms using the Avogadro number, and that in this case it does not apply. Hence I have these two questions. First question says calculate the number of atoms. You see, so for us to calculate the number of atoms, what does it mean? It means I must go back now and use the Avogadro number, because the Avogadro number gives me exactly the total number of atoms in C4H6. But a different question now comes. calculate the percentage composition. Percentage composition will now be what? How much of carbon contributes to what? To C4H6. So I am only going to work with the number of 4 carbon atoms. I am only going to work with now what? 6 hydrogen atoms. But if the question says calculate the number of atoms, I am basically working with now what? Everything which is now C4H6. So if that is the question, definitely, then I must use the Avogadro number. But if the question says calculate the percentage composition, I'm only interested in the arrangement of atoms. That means how many atoms? 4 carbon atoms that I have in this C4H6. So the only thing that will differ, such that we don't get confusion, is when we talk of percentage composition, we basically talk of how each element contributes to the compound and how many atoms of this particular element contribute now to the compound. But if it's the number of atoms, calculate the total number of atoms, it basically says now I must start using the Avogadro number. Hence the basics of everything we did last week. So I want now to open my chat. I think I tried to assist you, sir.
Yes, thank you, sir.
Thank you very much, Your Excellency. There are 2 questions here. I'm going to address them quickly because we still have a lot to do here. Manuku says, sir, will there be a case where they don't specify which element do we use? Okay, fine. Manuku, if they don't specify, it basically says you calculate for each and every element that is in that compound. So now for the case of Cu, I said let's copper sulfate. I said let's calculate for Cu. But the question, if we was just said determine the percentage composition of the following, we're supposed to calculate now for copper, calculate for sulfur, calculate for oxygen, add the total, get now 100, then we know that we have calculated for everything. So even if you check the question itself, it says determine the percentage composition of the following. So basically what they are saying is calculate for each and every element. So I did not want to waste our time because remember, I'm just now stressing the approach to this particular question. But in an exam, obviously they will specify. But if they don't specify, it basically says you calculate for each and every element that is there. Then let me answer Musa. Musa says, so the percentage composition is the calculation behind the fact that nitrogen comprises approximately 78% of the oxygen in the atmosphere. Oxygen is taking 21% and the remaining gases is 1% of the other gases. Musa, you are 100%, because remember what we have in the atmosphere, or what we call air, is we have different gases, but those different gases, they must now comprise now of 100%. So the 100%, the 78 will be for nitrogen. The 28%, is it 28 or 21? I don't remember. That's natural science, that's geography. Maybe some of you are still exposed to that, but generally that's what it is. Everything that makes that air, all the gases, they must add up to 100. So it's basically the percentage composition. So if I were to calculate now for copper sulfate or potassium permanganate, then my final answer, or the sum of everything thereof, must be 100%. So Jerry is saying, so say if I get 99.99%, will I be penalized? Hi Jerry, let's leave that one to the examiner and the discretion of the marker. But I don't think they will penalize you, sir. because to the nearest 10 it will be now 100%, but ensure it's 100%. So the easiest way of solving this problem is never round off during your steps or between your calculations. Just round off at your final answer. That is now the hint that I am giving you. Guys, I think we have exhausted the issue of percentage composition. I want now, or like us, to go to this one here. Thank you. So now this one, we are interested now in the empirical formula. Empirical formula. So the question is, what is this empirical formula? Empirical formula from grade 10. We know empirical formula as a formula that indicates the simplest ratio in which elements and compounds are bonded to each other. So I'm going to write that down. I'm going to write that down. Okay, empirical formula indicates the simplest ratio in which the elements of a compound are bonded to each other. Full stop. The difference between empirical formula and percentage composition is very simple. Percentage composition, how much each contributes in the formation of the compound. What percentage? Empirical formula, how are these atoms arranged or elements arranged to form this particular compound? It's as simple as that. Hence, it's explained as the simplest ratio. What is this ratio? Simplest ratio, the atoms here is 4:1. The one for C4H6 was 4:6. This one of copper sulfate was 1:4. So that is what the empirical formula is telling us. The simplest ratio in which elements of a compound are bonded to each other. That's how simple it gets. Now, I have steps here that I wanted us to look into. So, these steps are steps that we need to follow. But before we get to the empirical formula, there is a step that I want us to add, which is now number 7. The number 7 is now getting the molecular formula. But this is just a bonus thereafter. How is it a bonus? It's a bonus because some information relating to this molecular formula will be given. So from the empirical formula that I have, I can easily now be able to get the molecular formula. So be on the lookout, because we are now in grade 11. The question might not necessarily want us to work with empirical formulas. The question will be determine the molecular formula of this particular information that will be given. So it means you must perform all the steps from 1 up to 6 and then add number 7. So step 1 says we must always assume that we are working our mass in terms of 100-gram sample. We must always assume. So if you are given mass, then it means that mass must be converted to the number of moles. If we are given a percentage, that percentage must be converted to the number of moles. So basically, at the end of it all, where do I start? My starting point will be what information is given to me. If I am given mass in terms of percent, it's easy for me now to convert that into my mass. If I am given the mass, already I must just calculate the number of moles. Check how this is arranged. The mass, if is given in percent, then you must just divide that by 100, or automatically it will be you will be converting it, because that will be in 100-gram sample. So basically, if you have now 35%, it basically says in this case it will be equals to 35 grams. That is what assume the 100-gram sample basically means. But now if I already have the mass, this point, this is now if mass is given. So already I must just now calculate now the number of moles. So after getting the number of moles, I draw up the ratio, divide now by the smallest number, obtain the whole number, multiply that ratio, and then it will give me my empirical formula. So for number 7, I will add it here. For number 7, for me to get that whole number, there's a number that I need to multiply with. So it will be now the molecular mass of the formula. That will be now molecular mass, molecular mass divided now by empirical mass. So the molecular mass, this will give us now the multiplier. Let me call it the multiplier. Is it right? Not right. This is multiply. Okay, multiply this, multiply the empirical formula. The empirical formula with the answer. 100%. It's as simple as that. But I must emphasize molecularness should be always given. Must be always given. This is key, such that I'm able now to divide, because I cannot be working with a lot of unknowns. So this is also from grade 10, guys. So if it's from grade 10 we only do up to 6. So for grade 11 we extend it now to 7. So if we extend it now to 7, it means we'll now need to be in a position of ensuring that we add now this particular step. There will be marks allocated for this particular step. So I believe it's clear, and the approach, we will all know how to go about it. So let me move now to the next slide, on next page. I think next page will be just an easy way of showing you how to get the empirical formula. I'll just do one example of this. History has taught me that we don't have much of problems with empirical formulas. It will be just an issue of how one explains in detail. So the question here says, determine the empirical formula of the compounds with the following percentages. So we are given the percentages. So remember, if we are given percentage, it basically says we have now 63.5 grams. We basically have now 36.5 grams of sulfur and now of iron. So how do I get the number of moles? It's easy. I already have the mass. So for me to calculate the number of moles of iron, it's easy. It will be M now over M. This will be 635 divided now by 56. Yes, it's 56. And then the final answer will be 1,13 mole. Then now calculating for sulfur, I'm going to use M over M, which is equals to the mass 36.5, and then as we agreed, it's something like 32 depending on the periodic table you have. Then you get your final answer as 1,14 mole. So already by so doing, we will give you something like 2 marks already. You'll get a 1 for substitution of 56, and then 1 for the correct formula. Only 2, guys, not more than 2 in this step. Then we further extend it. They said now step number 2, let's go back, refresh. Step number 3, we have the number of moles. Draw up a ratio. So let's draw up a ratio. Drawing up a ratio means I have iron into sulfur. I have 1,13 into 1,14. What do I do after setting up that? Divide by the smallest number. So dividing by the smallest number is dividing by 1,13, dividing by 1,13. I am still in that ratio. Thereafter, obtain a whole number. So if I obtain a whole number, this will be 1, this will be 1, then that is the whole number they are talking about. Then after obtaining the whole number, it means it must give me now my empirical formula. So I have my empirical formula, which is just iron sulfide. then I become very, very happy with my final answer. So I am leaving the section of step number 7 for the purpose now of the exam type of questions that we are going to have. So this topic is quite a lot, but I love how we moved because now our foundation is very solid. The approach is somehow different from what you have been exposed to at your school. So automatically you can easily see the way I do things is somehow different from how everybody else do things, but this is the easiest way and the simplest way for me now to ensure that everything is being done the right way. So I will pause a bit, give you something like 10 seconds for you now related to the empirical formula. If there's anything that you want to ask for the next, let me make it 15 seconds. Manuku, you can go ahead, Mac.
Sir, do we specifically use that formula?
Which formula?
The one you used over there of N into iron is equals to M over M.
For calculating the number of moles?
Yes, sir.
No, it can be anything. Remember, I will go there now. Let me remove this. Let me go back. Back, yes. Remember, we said for calculating the number of moles, hence we have this as number 1. Mole equations. You remember?
Sir. Yes, sir.
Yes. So now it means depending on the information that is given. So it does not necessarily say if I am given now concentration, I will not be able to get the number of moles, you see. But now the first step in that empirical formula is obtaining the number of moles. So how you get the number of moles, it will be determined by what information do you have. Remember, the question we are currently working with, we are given the mass. So the only way of us converting the mass to moles is through this particular equation. But if I was given now the number of atoms, which is number of atoms of iron, what was I going to do? Definitely, I was going now to use this particular equation here of n is equals to n is equals to n over na, as long as the key and the starting point will now be what? Will be getting the number of moles. So what you are saying to me, you are saying step number 1 here. Step number 1. I must now modify this particular slide of mine and add many other ways of getting the number of moles. Because if you can get the number of moles at 1, then it basically says 2 and 3 and 4, 5, 6 and 7 will still be applicable because we now know how to calculate the number of moles in so many different ways. So this example was now based and focused on when we are given the mass. Thank you, Nuku. Hope your hand was up.
Oh, yes, yes, it was up.
Yes, Hope.
My question was, while setting up the ratio, we
Yes.
divide by the smallest number. So 1,14 divided by 1,13 is not exactly 1. What about the other decimal numbers? What do we do about them? Do we just like omit them?
Okay, give me the decimal numbers there. What you have is 1 comma.
1 is 1,0088
884.
for that.
That is where now the rounding
Yes.
off comes in, you see.
Okay. Yes, sir.
Yes. So now, because even if you round off here, you'll only get 1,001, which will not necessarily influence the final answer.
Oh.
Yes. But if
Okay.
we
Okay. I
got
see.
something like 1,9, because remember, it says here we must obtain a whole number, not a decimal number, but a whole number at now step number 5.
Okay.
Thank you very much,
Thank you.
sir. Then you can switch off your camera then. 100%. Any other questions? Clear on this one. So let's take one quick example. The example here, let's move on. Or is the example, that's the one we did most. So we are done with that one. Guys, the next 30 minutes, I fully need your attention. Drop everything that you are doing and kindly give me your ears for the next 30 minutes. The next 30 minutes is the science. Is the science that, as one of the examiners of these papers or grade 11, 10 and 11 physical science, we have a challenge and a very huge challenge when it comes to this slide number 15. Slide number 15 works with the whole chemistry. Slide number 15, it's the chemistry of everything we did last week, everything we did today for the past 90 minutes. So sorry. And slide 15, you will forever need it as long as you are doing chemistry in South Africa. So slide number 15 gives us the approach. And this approach, hence I said I am going to modify it for the next session. I feel that in the next 30 minutes, I wouldn't have done justice to this particular chemistry. So I am going to arrange a special session for us in order to try now and maximize and be ahead of everyone that is not part of the program. So this section here is the section that will differentiate you at your school from each and every other child that is not part of the program. Ndate Nambane, what are you saying? I am saying all the questions that are going to come in an exam, in most cases, will follow this particular approach. But there's one key thing that we already know. We already know about balanced chemical equation. So once I am given a chemical equation, before I can attempt to answer, that chemical equation must be balanced. It is your duty and responsibility to ensure it's balanced. If it's not balanced, then you cannot work with that particular equation. Number 2, molar mass of relevant reactants or products. This is now the chemist. It will depend on what you are giving. But I want us now to focus more on the reactants for now. So here at number 2, I want us also, maybe I must add it at number 3. Let me add it at number 3. At number 3, the first one is mass to moles. I am going to add A or B, which will be now number of atoms to mole. I'm going to add now AB, concentration to mole. C, I am going to add what is that other one? Volume.
Volume.
Yes, volume. So volume to mole. So what does this say? This says we are not restricted to working with the mass only. We can be given the number of atoms, the number of molecules. So once I have that, I must now convert that to the number of moles. What am I saying? I'm saying the chemistry, the knowledge that I want you to take home, your takeaway for today. It's ensuring that you are able to move from any chemical quantity to the number of moles. So if you are given volume, you must also be able to convert to the number of moles. The stoichiometry, the complex science that I spoke about, is based now on what? On the number of moles. So if you do not have the number of moles, ladies and gentlemen, your excellencies and your highness, if you do not have the number of moles, you will not be able to perform any other chemistry that will be in a question paper. So it was not a foolish move last week to ensure that you are able to calculate the number of moles for any given information. So the textbook or any other information that you have, it will focus more on mass to mole. But Ntate Nambane says, no, it can't be. We have so many ways of calculating the number of moles. So the number of moles that I calculate from using mass and the number of moles that I'm calculating using concentration is still the number of moles. So if it's the number of moles, it means I can be able to do the extended science. So if I have the number of moles, obviously 1, 2, and 3, and 4, check this, and 4, this will always be given. 100% will always be given. Why do I say it will always be given? The concentration of is equals to this in a volume of is that. Calculate the number of moles. That information is given. The mass of X is 25 grams. You check now the molar mass, you get the number of moles. The volume is now 25 at STP. The molar volume is 20 2,4 dm cubed, you get the number of moles. The molar ratio, where do you get it? You get the molar ratio from the balanced chemical equation. So I must say now the molar ratio from the balanced chemical equation. Simple. So all this information is given. Look at number 5. Determine the limiting reactant. That is where I am going. I did not say what is a limiting reactant. I did not say how you are going to do the limiting reactant. I showed you the science that we have done already. I've showed you the possibilities of now answering questions regardless of what you need to do. But what is a limiting factor? What is it that is going to give me the information or be able to answer the questions? It's the simplest thing. Is this thing that they call the limiting reactant. Let me get a highlighter and emphasize that the limiting reactant influences the amount of product that you get. Limiting reactant allows us to bridge the gap between what? Between the information that is given and the information that is an unknown. I'm going to pause and allow you to take a breather or ask something related to this 1, 2, 3, 4, and 5 for the next 10 seconds.
Sir,
Yes.
sir,
Let me check who's talking or who's saying something. It's
Tia.
Tiamo. Yes, Tiamo.
Yes, sir. Can you repeat on that about the limiting or
Reactant.
reactant?
I will go there, sir.
Yes.
Thank you very much.
Thank you, sir.
Any other question? Musa? Jerry Thomas.
No.
Oh, Musa. Okay.
I was just about to ask the same question about the
Limiting reactant.
reactants.
Thank you very much.
If
Tiamo, your hand is still up. Do you still want to say something?
No, sir, I'm done.
Okay, thank you, Tiamo. Then lower your hand. Jerry, I missed you today. How are you, man of my age? Your Excellency.
Sir,
Yes.
sir, I'm okay. I'm okay, sir. And you?
Aye, 100%, brother. I can't complain.
Okay, sir. Teacher, I'm a little bit confused, you know, because I've once done these stoichiometric calculations. So I want to know, in other words, you're trying to say, if you want mole from another, and on the product or on the reactant side, you must use mole ratio.
100%. Mole ratio will be, let me do this first. Mole ratio will be a link from determining from the number of moles I have and determining the limiting reactant. We are not yet below the limiting reactant. Ne? All I'm saying is we do number 1, which is the balanced chemical equation. We do number 2, which is now identifying the molar masses. But now, if we have identified the molar masses, it forces us to use N is equals to M over M. Ne? Because we must calculate the number of moles if we are given mass. But I further extended it to say, no, this cannot only be the way of calculating the number of moles. We can calculate the number of moles even if we are given the number of atoms. We can calculate the number of moles even if we are given the concentration. We can calculate now the number of moles if we are given the volume and whatever gas we are working at with it's at STP. So basically all I was saying in the rate was now we need to calculate the number of moles. But
Sir, okay.
after getting the number of moles, what do? We use the molar ratio of reactants, né? That is now at step
Okay,
number 4 to determine the limiting reactant.
Okay, sir.
Yes, sir. So I'm going
So,
to do an example of 1 to 5 and then everything that is below, we will see how we link it now with our limiting reactant. So allow me to say to you, do you understand 3 and 4?
Yes.
Thank you very
yes,
much.
sir.
Then let's pause there and then we will build now to 5 in just a few minutes. Thank you.
Sir,
Jerry, Retabile and
sir,
Tabise, you are noted, ne? So let me finish with Jerry. Yes, Jerry.
sir, let me say you are given the mass of one reactant and you are also asked to find the volume of another reactant. So you use mole ratio.
You use mole ratio, say 100%.
Okay, sir.
So in simple English, thank you. So in simple English, mole ratio is a link. Maybe I must write it down. Retabile and Ntabise, you are noted. Let me just emphasize this quickly. I must add here to say molar ratio. I call it bridging the gap. Bridging the gap. But the gap between what? Between the known to the unknown. Unknown. That is where the molar ratio comes in. So if I am given this information, how do I link it with the question? I can only link it now through bridging the gap or crossing the bridge. You can say all these nice words, but at the end of it all, we want now to move from the known to the unknown. So how do we move that? How do we link the information that is given to the information that is being asked? The question is asking me about X, but I have information about Z and Y. So how do I link all this? I calculate information of Z and Y or ZY, link it now through molar ratio, and after the molar ratio, I have now information of the unknown. Thank you very much. Retabile, let me start with you.
Good evening, sir.
Good
Sir,
evening.
So I wanted to clarify, is mass still conserved with regards to the limiting reagents?
It's still conserved because remember everything of ours in this case, especially for chemistry, we want to do it in a closed system. So a closed system is a system where we don't allow now any mass to be exchanged with the environment. So the mass must also be conserved 100%.
Okay.
Thank you.
Thank you.
Ntabiseng Chabalala.
So I was asking if under the fourth step where the mole ratio of reactants, are we going to leave them in the formula unit of mole, or are we going to change the reactant into the empirical formula?
You must work with moles. Remember the information you have from step 3, it's based on the moles. So you only work with the moles.
Okay, thank you, sir.
Thank you very much. Musa, kindly switch off your mic. Thank you very much. So guys, in simple terms, simple English, you need the number of moles. The number of moles is your basic starting point. After getting the number of moles, you use the molar ratio. But what do we need the molar ratio for? Is for bridging the gap. The molar ratio or mole ratio is what allows me now from the known to the unknown. So sad. Let's move on. This is the basic I want you to get for now. Let's move. Here is a question. Read it and analyze. Aluminium reacts with oxygen. The balanced chemical equation is aluminium plus 3 oxygen gives us aluminium oxide. I'm going to write it down. Which substance is a limited reactant? I don't know. You must prove. That is the science. If something seems to be complex, we find solutions for it. But we need some information. So this information must be from where? Step 1, step 2, step 3, and step 4. That information is already given within the statement itself. So step 1, balanced chemical equation, which is 4 aluminium plus 3 oxygen gives us now 2 aluminium 2 oxygen 3 aluminium oxide. Is it balanced? Yes. So step 1, check. Step 2, sorry. Step 2, molar masses. Do I really need molar masses? No, I don't. Why? Because I am already given the moles here. You see. So if I was given mass, I was supposed to calculate the number of moles. If I was given concentration, I was supposed to calculate the number of moles. If I was given the volume of aluminium and oxygen, I was supposed to be now in a position also to calculate the number of moles. So I don't want us to be limited or to be stereotyped into thinking that the only way of calculating moles is through mass. So the slide was chosen with purpose, such that I can be able to emphasize that you will see more of this in your textbooks, your teachers maybe also, but remember somewhere at the back of your head that we still need A, B, C in order to get the number of moles. So this information is given. Which substance is a limiting reactant? Step 1, calculate the number of moles. So I have number of moles of aluminium, which is equals to 3 mole. And then I have number of moles of oxygen, which is just 2 mole. That is given. Now, after that, molar ratio. what is the molar ratio here? Let's assume that aluminium has been used up. So I am going to work with aluminium and I will work with oxygen. So if I assume that I am going to work with aluminium over the number of moles of oxygen, this one is what I say it's needed. Then I know that I have the molar ratio is 4, yeah, molar ratio. It's now 4 over 3. Then I do the science here. I know that I'm working with aluminium, so I have 3 over oxygen, which is equals to 4 over 3. Then I know this will be 4 NO2. This is now 9. Then I divide by 4, they cancel there. I have now O2, which is equals to my
3 over
calculate.
2.
Is it 3 over 2?
Yes, sir.
So 3 over 2 is 1.5 mole. .5 mole. Close this. Tiamo, you are noted. Let me just write my final answer. Computer, guys, computer. Tell your parents there to invest in me there, please. 1.5 mole. But remember, this is what I said we need now for the reaction to take place. This one is the one we need. So initially, noted Siamo coming. Initially, we have 2 moles of oxygen, you see. But for this reaction, or to use aluminium completely, we only need 1.5. So it says I have now the 0.5 mole of oxygen that is left. So what does this say? It says now oxygen is in excess because I still have the 0.5 that is now pending or that did not react. Siamo, the stage is yours.
Sir, thank you. So I was asking, there 9 over 4. If you say 9 over 4 is equals to 3 over 2, it means you use the square root there, sir. So I don't think it has to be 1.5, it has to be 2.25.
I was waiting for you. You are the ones with a calculator, say. Hey. And I got the answer from someone in this particular group. Let me trust myself and use my own calculator. You see the things you do now. 9 divided by 4 is 2.25, you see. So somebody said 1.5 and I didn't open my calculator. You see now class. This class. Thank you for the correction there.
It's my pleasure.
Thank you, Your Excellency. 2.25 mole. Thank you. You see, just a simple mistake of a calculator can now influence everything, because now I was referring to the answer you guys gave me. Yeah, guys, come on. Thank you. Now, If the answer is 2,25, now it changes everything. But before I can conclude then, let me now try and say, let's say now we assume that oxygen is the one that is now completely used up. So I'm going to work with oxygen. Now I need now aluminium just to check how much do I need. So the ratio there from the balanced chemical equation, 3/4. What is my number of moles now of oxygen? 2 over the aluminium that I need, which is equals to 3/4. Then I do the maths, is 3 aluminium into 8, divide now by 3, divide by 3, then N of aluminium, because I don't trust you anymore. I am going to open my calculator, which is 8 divided by 3. It will give me something like 2,67. 2,66 ne, or 67. 2,67 more.
Sir,
Yes,
sir, can I ask?
you
Sir,
can.
I'm confused, sir.
Okay, I'm going to explain now. Just waiting for this
Sir,
thing to respond, and then I write my final answer.
okay.
I'm with you now, don't worry. More. Fine. Now I have, let's call this one option 1. And then I call this now option 2. I'm going to explain option 1 and allow questions or option 2. With option 1, the assumption here was aluminium is all used up. That is what we need to assume. The difference here was we assumed that oxygen, O2, is all used up. So one will ask, in an exam, do I go for option 1? Do I go for option 2? Honestly, it doesn't really matter. What will matter at the end is how you interpret the 2 final answers you have. So I have my number of moles. So remember, once I say 1 is used up, the 1 must be the one that I need, or the one that is needed for the reaction to take place or to complete, or basically how much reacted. That is what we are saying. So how much of oxygen do we need for aluminium to react completely? How much now of in this case of aluminium for option 2 do we need such that it can react completely with oxygen? So the option is entirely up to you, but the key thing is we are working with a reactant. So now I'm going to take questions. The question here from
Okay.
Ritabile, wait, you must raise your hand first, because I said I'm taking questions. So for the purpose of order, I'm starting with the chat, then we'll come in. Why are we calculating the number of moles if they were given to us. Very true. The number of moles, remember, it's the initial number of moles, Retabi. So we need something to compare with. So basically, let me put this here. This here is our initial number of moles. This here is our initial number of moles. So this is the beginning number of moles that we have. So why do we need to calculate the other number of moles? We want to know how many of the 3 moles do we have that we started with actually reacted in this particular reaction. How many moles of oxygen exactly reacted to form our product? Remember, in a reaction, it does not necessarily mean everything will react. So we start with 3 of aluminium, we start with 2 of aluminium, of oxygen. But we want to know, for aluminium to react completely, how much of oxygen do we need? So we need 2,25 moles of oxygen. So for this reaction to take place completely, we need now what? 2,2 moles, 2,25 moles of oxygen. So we are only calculating the number of moles again. This one is now what? Reference in terms of how much do I need. So I have the 2, but I need the 2,25. So what does this mean? It says my oxygen is somehow limited. My oxygen is not enough. My oxygen will not be in a position of giving me the final desired product. So that is the reason why, Ritabile, we need to have some form of reference. So the number of moles that we are calculating here at step number 3 using the molar ratio is basically us now trying to bridge the gap between the known and the unknown. So in this case, what is the unknown? The unknown is how much do I need for this reaction to take place. So for option 1, I need oxygen of 2,25 mole. Do I have that much? No, because I started only with 2 moles. For option 2, I need aluminium that is now equals to 2,67 mole. Do I have enough? Yes, I started with 3. So it means I have a remainder somewhere. I am taking questions now for those who want to voice their opinions. Raise your hand, then I will attend to you. Tabile, I hope it makes sense. We need reference in terms of our starting point, in terms of how much do we need. So the how much part of what we need, we link that with the molar ratio. Anyone who wants to say something? Let me have my timer here, so that you know that I'm giving you 15 seconds. Let's go. May you please explain the calculation? Okay. Okay. Thank you. Guys, there are many ways of killing a cat. This was just a simple step that I can give you. That one that you are doing at school is complex. Or maybe you understand it better because you work with your teachers daily. It's true. We approach it differently, but ultimately we'll get to the same answer. So the plan is I'm going to give you that method you also have from your school. So that is option number 3 and option number 4. You see? So Ritabile, prepare option number 3 for us and explain in detail how you do it at your school. While you do that, I'm going to allow some other questions here. May you please explain the calculations? Kamuhelo Mahau, I think I did that. If I didn't, then we will go back, or we'll get an option number 3 now. That is from Retabile. Thank you for understanding. So does this mean oxygen is the limiting reactant? We will come there. Now lady is asking, so say the limited reactant, is it aluminium or oxygen? Now lady, kindly analyze the two calculations, ne? And decide on the answer. We'll answer you now. I'm going to take hands. I saw a hand from Jerry. Yes.
Sir,
Yes, Jerry.
in other words, I'm trying to say, before these two reactants were mixed in a chamber, there were 3 moles of aluminum and 2
Yes.
moles of oxygen.
100%.
So when they were mixed in a chamber, only to find out that 2,25 moles of oxygen, it's one a functional.
That's what we need.
It's one, yeah, they're required in order for the reaction to take place.
Exactly.
Okay, sir.
But now do you see that we don't have enough? We need 2,25, but we only have 2. But for option 2, because we are working with aluminium there, ne? Aluminium, we started with 3.
Yes.
We have we need 2,67. So it basically says aluminium is in excess. I have more than enough.
No, sir. I disagree, sir.
Okay, it's fine. Let's hear what others say. I saw Tiamo, you wanted to say something.
No, it's fine.
How is it fine?
I wanted to ask how do you see which one is the limiting reactant after your calculations?
Okay, thank you very much. Hey, Mipon, you are sending messages here about sympathy, so I don't know how it relates to limiting and all this. I honestly don't know. Mipone Letswaka. So please, if sympathy is what you want to show, try to show compassion. Oh, your hand is up. Oh, okay. Miponi Letswaka, the platform is yours. I'm still shocked about the sympathy words you wrote there, so I'm trying to give you the platform in terms of feeling sympathetic for you. Mipon.
Sir,
Yes.
sir, I was trying to ask you that don't we use like the coefficients or the mole ratio?
The coefficient is the mole ratio. Hence I used 4 and a 3.
But then, sir, didn't you use them to calculate the moles?
No, I used them to link the number of moles that I have with the molar ratio. So 4 and 3 is the molar ratio.
Okay, sir.
Yes. From where? from the balanced chemical equation.
So, sir, based on how the question is asked, what are the max allocation?
This one can be 4, but the other ones that are coming, it will be 2 marks or 3 marks.
Okay, so let us say maybe it's a mark, say. So if it's a mark, like we already given the moles, so we can just decide that it is the oxygen.
That's not true. That is very wrong.
I'm just asking, sir.
Yes, I know, and I understand. Thank you for bringing up Miponi. Now I'm feeling very sympathetic for you. Miponi, the number of moles, we have 3 and 2, is basically the initial number of what I am starting with. For me to determine which one was a limiting reactant, I need to know how much reacted or how much I need.
Okay, sir.
So because you will, next time somebody will say, but now if I have 25 grams and now 50 grams, so automatically, because of 25 is smaller than 50, it says 25 must be a limiting reactant. It's not true. That's not how it is.
Yeah, I understand, sir.
Thank you. So what do we need the 3 and the 2 for? We need the 3 and the 2 as our base, as our initial number of moles. So guys, this thing is simple. I want, let me have a new page here.
Please.
Let me have a new page. Retabile, you must still preparing that option number 3 for us.
So must I do it the way we do it at school?
Yes, you must do it the way you do it at school, but not now. Let me just try to explain the basic things of how to understand this. Let me add a page. Now, this is a fresh page there. Guys, I want to have 1, 2, 3, 4, 5, 6 muffins. Or because all of us are familiar with 6, the number of muffins, let's say we want now to have 24. It's 24 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. This is the final product that I want to get. This is the muffins, Sharp. I'm moving away from science, but trying to explain this concept. Guys, what do I need? For me to have the muffins, I need maybe 500 ml of sunflour. Plus, I need 8 eggs. Happy. Sunflower is cooking oil, Let me say cooking oil for everyone to understand. Happy guys. This is what I have. 500 ml of cooking oil, 8 eggs. but I want to get 24 muffins. Is it possible? I have 5 ml of cooking oil plus 8 eggs, but I want to get the end result, which is 24 muffins. Is it possible from what I have written now? It's not possible, ne?
No.
It's not. Fine.
Why?
Because how will I have the powder that will give me now the muffins? Because this is just water on water. It's oil and eggs. So how will muffins be formed there? Yeah?
Yes.
It's oil, cooking oil, fish oil, and eggs. How will that give me muffins? They are not, ne? And how will the 500 ml cooking oil and eggs exactly give me 24 muffins? There is no way. There is something that I need. Ne? That, what is that? I need what they call a muffin mix. I need what they call a muffin mix. Okay? Because the muffin mix will come in different flavors. It will come in what is this? Vanilla, cappuccino, depending on what you prefer. But all of them will still say, I need 500 ml of cooking oil, I need 8 eggs. So what do I know? I know that muffin mix. So I know that one bag, which is 1 kg, gives me now 24 muffins. And I know now that if I use half, which is now 500 grams, is going to give me now 12 muffins. Ne? So here comes my problem. I am at my house or at home, but I only have now a muffin mix which is 500 grams. Then I am going to put it here plus as an extra reactant. So I have 500 grams of muffin mix plus 500 ml of cooking oil plus now 8 eggs. Will I get the 24 muffins from using the 500 ml? 500 gram of the muffin mix. Will I get the 24 muffins, guys?
I hope so.
No. So in this case, we say muffin mix, the one that I have, it's not enough. So if it's not enough, it becomes my limiting reactant. What is it that it is limiting? It is limiting the outcome of the number of muffins that I am going to have. But if I have now 1 kg and I decide to use the 1 kg if I put the 1 kg here, the 1 kg according to the recipe should now give me what? The 24 muffins. So 1 kg is enough. It's not in excess. It's enough to give me the 24 muffins. But I decide now to say, let me not use the 1 kg, but I am going to use the 2 kg. But what do I need? I only need 24 muffins. I don't need more than that. Because now the number of eggs that I have, the sunflower that I have, only allows me to have now what? 24 muffins. So if I put now the 2 kg of muffin mix, the 2 kg of muffin mix will now say what? Will now give me 24, and I will still remain with 1 kg. So what does this mean? It means now if I use the 2 kg, I am going to have 1 kg that is extra or that is more. So in this case, eggs and cooking oil becomes my limiting reactant because I don't have enough to accommodate the 2 kg. I'm going to repeat. If I have the 500 gram muffin mix, of which I need for muffins to be formed. But according to the recipe, for me to get decent muffins, if I want 24 muffins, I must use 500 ml cooking oil. I must use 8 eggs. But now the only muffin mix I have is only 500 grams, which can produce 12 muffins. So when I use the 500 grams, it is now becoming a limiting reactant because I can only produce now what? Only 12 muffins. But the idea is I want a total of 24. So what am I basically saying? All I am saying is your reactant, the one that is in excess, it will be a leftover. So I did say I am starting with 1 kg. So if I'm starting with 1 kg, 1 kg will produce the 24. That will be just enough. But once I decide now to use 2 kg, it means I have more than enough muffin mix. So the eggs that I have and the cooking oil that I have, it's not enough. So the eggs and the cooking oil becomes my limiting reactant because they are insufficient. I only have 8 eggs. So let's go to the science. I only have how many? 3 moles of aluminium. I only have now 2 moles of aluminium. What is this calculation for option 1? This calculation for option 1 is basically says how much do I need in order to have now what? Full complement of aluminium oxide that is produced. So me saying we need to assume that this one, which is aluminium, is used up. So these are my eggs. This is my cooking oil. That is only thing that I have. But I want to check how much sunflower, which is oxygen, do I need? You see? So the oxygen that I need for me to use up all of aluminium, I need 2,25. Do I have the 2,25? No, I don't have the 2,25. I only have the 2. Hence the science of simple saying, what is it that I have? I want to produce this much, 24, but I only have 500 grams. So it's in the muffin, nowhere. Because now the 500 gram limits me to only have now what? Only 12 muffins. But if I have the 2 kg, I will even have more. But the eggs that I have are limiting me. They are not allowing me to have full complement of the products that I want. So the limiting reactant limits the product, the amount of product that is being formed. So I start with 3 moles of aluminium. I start with 2 moles of oxygen. Nice question. Which one is a limiting reactant? We all know we are going to produce aluminium oxide. We all know the balanced chemical equation is there. So I need to know which or how much of oxygen do I need. Hence I said this one we need. Why do we need this one? Because the assumption is we need now between the two to assume that one is used up. So if I have my 8 eggs and I have my 500 ml cooking oil, that is all that I have. So those ones will be used up. But I need to know how much flour do I need. So the flour that I need is how much? It's 2,25 mole. But I don't have that much because I only have 2 moles. Am I going to get sufficient product as per required? No. So the science here is very easy to say. How do I link the two? I link the two by using the molar ratio. And I did say the molar ratio comes from where? From the balanced chemical equation, guys. Questions? Jerry?
Teacher, according to Wena, which one is a limiting reactant?
Wait a bit. We are coming there. Remember, we still have that option from Ritabil.
Okay.
Other hands, the chat is empty. So Ritabile, if the chat is empty, I'm going to try and follow your procedure, so that you can see at the end that we get the final answer. So kindly unmute your mic. I'm going to add your option here, which will be option 3. So let me make space for you here. So this will be option 3. You can go on.
Okay.
Yes.
So I don't really know how this thing works, but I just took it as it is because it looks like it's not a formula, but it's just the way that our textbook just put it. So it said, obviously you would start off by balancing your equation.
Yes.
Everything must be in moles, obviously. Yes. And then you can use your mole ratio to compare. In this case, they gave you the moles. And then the next step would be to say the number of moles of your first reactant.
Which is aluminium.
Yes, it's aluminium. Yes. And then divided by the number of moles of oxygen. Your second reactant, which is oxygen. And then you would compare it with the coefficients
You will say it's equals to.
thereof. Yes.
Do you
No,
say
no, no. Well, it says over here if it's bigger than. So if the
I want to write it the way you will write in a test, so that you can get marks for it. Ne?
Oh,
So what do I
okay.
write after this?
So I said it's equal to AB.
Is equals to A over B.
Yes.
A
which
over
represents coefficients.
B. So now aluminium.
Yes.
Okay. Then you further move on and set.
And then after AB, I said it's equal to 4 over 3.
Is equals to 4 over 3. Okay.
Yes. So that's the coefficients. And then, yeah, and then I said basically the number of, so I don't know how to explain it, like if you're writing it, if you are writing it.
So now you are at the final exam. You must get 4 marks. So my question is, how would you write it so that I can allocate marks to you?
Okay.
That is what
and
I
then
want.
After that,
yes.
Okay. And then after that, I wrote N, the number of mole of, well, not next to it, like under it. So.
Okay, under it, it's N. Okay, let's wait for this thing to respond. If there's somebody else with a different option, kindly raise your hand and then we'll attend to your option as soon as I am done with Retabile here. Okay, Jerry, you are noted. Wait, this system here, it's complex. It's taking time. It's not flexible as I want it to be. Okay, it looks like it's getting there. Okay, there is your N.
So, but like on the left hand side.
Okay, on the left hand side, there's another N. There is your N.
So, but like it's fine. Like I understand your method. I think I like your method better because this one doesn't really explain. It just looks like it's just giving you things to do.
Okay, so
like I'll use your method.
Should we write it off? From your method, what is your final answer? Maybe if we can write your final answer. Which one is a limiting reactant?
Oxygen.
Oxygen. So you said OR02 is a limiting reactant. Jerry, I am giving you now option 4. Thank you, Retabile, very much for your inputs. You got to the final answer the way you did, but you were not in a position of fully explaining how you got there. Ne? So my worry is one. If you're going to write this in an exam, as an examiner myself, where do I give you marks now? I'm just going to give you marks here for just saying LR or is O2. Now you see the difference, guys. I want you to do things that you understand. And I did not say this one is right. Maybe it might be wrong. We still have to wait for another method. Jerry, you said you are sharing your method, ne?
Yes, sir.
I'm making it option 4, big brother. Just quickly. Thank you, Ritabile. We
are not trying to sleep.
It's what time is it? Oh no,
it's almost 10.
No, it's late. We will finish now in the next 2 minutes. I'm going to give you your final answer. Then we consolidate. Then we'll have another session where we'll explain this in detail. Jerry, the platform is yours, sir.
So first you will write N2, which represents the number of moles for oxygen, equals to A over B multiplied by N1.
Okay, don't rush. It's N over N of oxygen over
Equals
equals.
to, sir. Yes.
Okay.
A over B.
A over B.
N2. N1. So N1.
Wait.
N for aluminium.
So where do I say over?
You don't say over, just multiply on the right hand side next to A over B.
Okay, I must multiply here with now what?
N, number of moles of aluminium.
Number of moles of aluminium. Okay.
SnO2 is our subject of the formula.
So you make NO2 subject of the formula.
Yes, sir.
Okay, so it means you are working with oxygen, ne?
Yes, sir.
You are basically calculating the number of oxygen.
Yes, sir.
Okay, so your A will be your 4, ne?
No, it will be 3.
Okay, because you started with oxygen over 4, ne?
Yes, sir.
Multiply by the number of moles, which is 3 for aluminium.
Yes, sir.
So you end up with 9 divided by 4, ne?
Oh. Yes, sir.
And 9 divided by 4 is 2,25.
25 mole.
9. The computer, come on. You want to sleep, this thing.
Shall I proceed?
Wait a bit, people. I just know that your final answer will be 2,25, ne? So 9 divided by 4 is equals to 2,25 mole.
Yes.
So what does this say to you, sir?
Sir, I'm comparing.
What are you comparing?
I'm comparing the moles of aluminium and oxygen so that I can.
But remember, your answer here is for oxygen, eh?
Yes, sir.
Yes. So it means you are now in a position of comparing oxygen with oxygen.
No, sir.
Okay, continue, sir.
Then N of aluminium, number of atoms of aluminium.
Okay, you have other steps. So it's N of aluminium is equals to now A over B.
Yes.
A over B, number of moles of oxygen. Ne?
Yes, sir.
So this will be your 4 over 3.
Not. Yes, sir.
4 over 3 into 2. Then your final answer here will be 2,67 mole. Yeah, aluminium.
As you have just explained from your previous complicated examples, you said a limiting reactant is a reactant that is completely used up in a chemical reaction.
Yes.
So an excess is one that is not used up. So you will basically compare which one is more than the other. So according to my perspective, I think 2.67 is excess, then oxygen is limiting reaction because it's less than aluminium.
100%. So we can conclude, guys, and say LR, it's oxygen. From what Ntate Nambane said, LR is oxygen. Limiting reactant, it's oxygen. All these other methods, except yours, Retabil, because yours does not show me the steps of how you eventually got to the final answer. So if this is the case for Jerry, he's comparing the number of moles. But if you check this section here, let me get a red pen here. This section, it's my option 1. This section, it's my option 2. But I did not use this over A over B because it's things that I will not know or remember in an exam. What I used is, I just know that I am working with aluminium, so everything above here must be for aluminium. I am working with nitrogen, so the divide there must be everything related to the oxygen. The value that I get as my final answer, I am comparing apples with apples, Jerry. That is where you are going maybe to miss it a little bit. If you have calculated for oxygen, you only compare oxygen with oxygen, apples with apples. If you have now done it in such a way that you compare, or you want to compare aluminium, you compare aluminium with aluminium. So you cannot move between comparing aluminium and then comparing now the oxygen. So if you work with aluminium, work with aluminium. If you work with oxygen, work with oxygen. And then at the end, you only compare the initial of oxygen with now the needed or the reacted, yes, the one that we need for oxygen. If we work with aluminium, we get the final number of moles of aluminium, so we compare the 2,63 with only the 3 moles of aluminium. Remember, what did I say when we start? I said I don't want to lose you, but this slide is the science.